Welcome to Chapter 11. This video is over Section 11.1, Sequences and Series. Here are the objectives for this section. We'll be writing terms of sequences using factorial notation and learning about summation notation. Before we get started, let's address a little bit of vocabulary. A finite sequence is a sequence whose domain is a certain number of terms, so it ends. Whereas an infinite sequence goes on and on and on and on, and it will be a set of positive integers in this course. The terms of a sequence are denoted with a lowercase letter and a subscript representing the number of the term. So this is the first term, second term, third term, and this is the nth term. Okay, so now we are able to get to our first example. And you can just ignore these graphs here for a second, but it says write the first four terms of the sequence. So in this class, we're always going to start with n equals 1 for our first term. So our first term will be found by plugging in 1 for n. So 1 squared is 1 plus 5 is 6. So the first term of our sequence is 6. To find the second term, we plug 2 in for n, plus 5. So we'll have 4 plus 5, which is 9. So 9 is the second term of our sequence. And we just move on. So here we have 9 plus 5, which is 14. Plugging in 4 squared plus 5 is 21. So if I were to write this as a sequence, we would say 6, 9, 14, 21, and so on. What we've done here is we have plotted each of the terms, and it's just illustrated here. Okay, here's our second example. Again, we want to write the first four terms given by this information here. So we will start with 1. So we have 3 times negative 1/3 to the first. This results in a negative 1. Our second term is 3 times negative 1/3 squared. Well, anytime we square a negative, the outcome is positive. So we'll square each of these. So this is 1/9 times 3. This results in 1/3. The third term of the sequence, we will plug 3 into the exponent. So this odd exponent makes this remain negative. So this will be a negative 1/27 times 3 gives us a negative 1/9. And then finally, when we plug in 4, we'll get a positive 1/27. Now something I want to point out is how the sign is alternating in this particular sequence. We have a negative, then a positive, a negative, and a positive, and this will continue. And I want you to notice that in this particular case, anytime we have a negative result, the exponent is odd. And this is something common that we will see in sequences. So on this slide, we are going to address what happens. So the example on the previous slide is known as an alternating sequence because the signs alternate from positive to negative. So there are a couple different ways in which these alternating sequences can be represented, but I'd say the most common is this one here. And this is where the odd numbered terms, so the first term, first term, third term, fifth term, so on and so forth, are negative, and then the even numbered terms are positive. Now, if you want to switch this, so you want the even numbered terms to be negative, then it would be written like this. So that means the second term, the fourth term, the sixth term, so on and so forth would be negative. Could be represented in this way. Also, sometimes this is written as -1 to the n minus 1 power instead. So either of these would be where the odd number terms are positive and the even are negative. We will see sequences that are defined recursively. And basically what that means is we will have a sequence that requires the outcome of the term before it in order to find the value of the next term. And the Fibonacci sequence, if you're familiar with that, is one of these very famous recursive formulas. Let's look at an example of what this means. Okay, so here we're given two pieces of information. Turns out we're given the first term, but then we're given this formula here, and we want to find the first four terms. Well, we already know the first term is 3. Now, if I want to find the second term, anywhere I see an n, I'm going to replace it with a 2. So the second term is equal to 4 times a to the 2a sub 2 minus 1. Well, 2 minus 1 is 1, and then minus 2. And so you can see here that we need the result of the first term to find the result of the second term. So all I'm going to do is plug in this previous result into this formula. So 4 times 3 minus 2 gives me 12 minus 2, which is 10. Okay, well, if I want to find the third term, then anywhere I see an n, I'm going to replace it with a 3. So this becomes 3 minus 1, which is a sub 2. Well, a sub 2 we know was 10. So this becomes 4 times 10 minus 2. 40 minus 2 is 38. All right, moving right along. Now I want to plug in the third term. When I plug the third term in, I end up with 4, let's be consistent, 4 times 38 minus 2, and this gives me 150. So the first four terms of this sequence is 3, 10, 38, and 150. Pause this and see if you can do this one on your own. This one is also a recursively defined sequence because this tells me that I need to know the value of the term before it in order to find that current term. The first term is given to us, so we are going to use that to find the next term. So the second term is found by taking 3 times the first term minus 4. So 3 times 5 minus 4 gives us 11. The third term is found by taking 3 times the second term minus 4. So 3 times the second term was 11, then we subtract 4. 33 minus 4 is 29. The fourth term is found by taking 3 times the term before it, which is the third, minus 4. So 3 times 29 minus 4 gives us 83. We do want to find the first 5 terms, so we'll find one more term, and we'll find that by taking 3 times the fourth term minus 4, or 3 times 83 minus 4. You're welcome to use a calculator if needed, and I believe you will get 245. I mentioned before that the Fibonacci sequence is a very famous recursively defined sequence. And basically, well, this here is the Fibonacci sequence, and it starts with the first term being 1 and the second term being 1. But then what we do is we will add these to get this. We add these to get this. We add these to get this, so on and so forth. And that's represented in this way here. Okay, so this is the Fibonacci sequence. Next, we come to factorial notation. And this is the math that you may or may not have seen, but it has the exclamation point. And it's important to mention that if we have 7 factorial, this does not mean 7! Instead, what this means is 7 times 6 times 5 times 4 times 3 times 2 times 1. And we stop at 1 because we don't want to say times 0, because anything times 0 is 0. So this is known as factorial notation. And a lot of times we will be using or seeing variables written in this way, like n factorial. So if I take this example and I plug it in here, this would be the 7. This is 6 because 7 minus 1 is 6. This is 5 because 7 minus 2 is 5, and so on and so forth. Okay? 0 factorial is always equal to 1. Let's look at some examples involving factorial notation. The first example we have is 5 factorial. This is equal to 5 times 4 times 3 times 2 times 1. Plug that into your calculator and you will get 120. Now the next one's a little more complicated because it's division. We'll just write it out. 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Well, you can make this pretty easy on yourself by noticing the 4's cancel, 3's, 2's, and 1's all cancel, leaving you with 6 times 5, which is simply 30. So you can make this easier on yourself. One thing I'd like to point out is that this is the same thing as saying 4 factorial. Additionally, we have a 4 factorial here. So if I have 6 factorial over 4 factorial, one way of writing this is 6 times 5 times 4 factorial over 4 factorial. And all of this is the same as what we have written up here in the blue. but the 4 factorials cancel out, and then I'm left with that 30. So just another way of writing this. Let's look at some more examples. This can be written as 9 times 8 times 7 times 6 times 5 factorial over 4 factorial times 5 factorial. This will cancel out. And then I can write this 4 factorial as 4 times 3 times 2 times 1. Nothing else cancels. Plugging this into my calculator, I get 3024 divided by 24. This results in 126. Now, example 7 cannot be plugged into the calculator, but let's just think about this. If I have n factorial, this is equal to n times n minus 1 times n minus 2, so on and so forth, over n minus 1 factorial. Well, I can rewrite this as n minus 1 factorial. In other words, this would be n times n minus 1 factorial over n minus 1 factorial. And these cancel, leaving me with n. Let's see how factorials are used in sequences. So if I want to find the third term of this sequence, anywhere I see n, I replace it with 3. So the third term of this sequence is 3 times 3 factorial divided by 3 cubed. 3 times 3 is 9, so in the numerator I have 9 factorial. 3 cubed is 27. So there is a button in your calculator that's the factorial button, FYI. So that way you don't have to do 9 times 8 times 7 times 6, so on and so forth in your calculator. You can just type 9, exclamation point, and then it will give you 362,880 divided by 27. This results in 13,440. Okay, now this is a little bit different. And what we want to do is we're given the first 4 terms of the sequence, and what we want to do is basically create the formula for it. So now we're kind of working backwards. So some students totally understand this and can do this right away. Other students kind of struggle. So let's take a look at this. Now, try to identify a couple things going on. Notice how I have alternating signs in this case. Since I have alternating signs and it's the odd terms, I know that I'm going to have this somewhere. Okay, so when n equals 1, I have a negative 5. When n is 2, I have 6. 3, negative 7, and 4, I have 8. So just ignore the signs for a moment and notice what happens to get each term. Now, if you ignore the signs, you'll see that we have 5, 6, 7, 8. So what we've done is we've added 4 to n each time and then attached this. So a sub n is equal to negative 1 to the nth power times n plus 4. And you can easily check this by plugging in these values and hoping you get these. You'll do the same type of thing in part B. Notice in part B, the numerator is the factorial. In fact, it's n factorial, the first term, second term, third term, fourth term. The denominator is 3. They're multiples of 3, notice, and it's actually 3 to the power of n, because 3 to the first is 3, 3 squared is 9, so on and so forth. So this formula is n factorial over 3 to the power of n. This may take a little bit of practice to get the hang of. Now we are getting to summation notation. Summation notation represents the sum of the terms of a sequence. So an infinite sequence, or a sequence that goes on and on and on, the sum is known as an infinite series and is represented by this. Whereas if I'm interested in only the sum of the first several terms, that's known as the nth partial sum and is represented in this way. The partial sum is a finite series because it's just sum of the terms. We will use the Greek letter sigma to represent a sum. So let's talk about each part of this. So sigma represents the sum, and here is an example of what this may look like. This little I here represents the index of the summation. This is basically the starting point. Okay, so we are going to start with the first term. So I is equal to 1. So it's the lower limit. Up here, this is the upper limit. This tells us where we are going to stop. So if this is a 5, that means we are going to stop at the 5th term. All of the terms in a sequence would have an infinity symbol up at the top and would be represented in this way here. Let's take some baby steps getting to become more familiar with summation notation. Here is our first example, and we want to write the terms of the series and then find that sum. So we are going to start with k equals 1, and we are going to end at 3. So this becomes 3 times 1 minus 8 plus 3 times 2 minus 8 plus 3 times 3 minus 8. Simplifying each of these parts, I get negative 5 plus negative 2 plus 1. So these are the 3 terms of the sequence. When I add those together, I get negative 6. So this sum is equal to negative 6. Let's try another one. Okay, we are going to start with I equals 1 and go to 4. So we'll have 2 times 1 divided by 1 squared plus 2 times 2 divided by 2 squared. Oops, let's do this. Plus 2 times 3 divided by 3 squared plus 2 times 4 divided by 4 squared. Then we will simplify each of these. So we will get 2 plus 1 plus 6/9, which is the same thing as 2/3, plus 8/16, which is a half. When I add all of these together, I get 25/6. Here's another one. So basically, anywhere you see a J, you will start with 3 in this case. So we are interested in the third term, fourth term, and fifth terms. So -1, 3 plus 1 times 3 times 3. Plus -1 times 4 plus 1 times 3 times 4. Plus -1 times 5 plus 1 times 3 times 5. Sorry, I ran out of space there. Okay, so this is for -1 to an even power results in a positive. So this term is 9. This is 5, so I know this next term is going to be negative because this negative to an odd results in a negative. So this is -12. This will be a positive because we have an even exponent, and this will be 15. Adding this together, we get 12. Now this one here is a little different, because all I have is this constant here. So what this is asking is the sum of the first 4 terms of the sequence when the sequence is just 10. So all this is 10 plus 10 plus 10 plus 10, just 4 times. First term, second term, third term, fourth term. This results in 40. Not so bad, right? Sometimes summations can be written in different ways. For example, if I have this, I can write that summation in these ways also, because writing out these first 4 terms, this gives me 1 squared plus 2 squared plus 3 squared plus 4 squared. If I look at this next one, something completely different, and now I'm starting with j equals 0, so this would be 0 plus 1 squared plus 1 plus 1 squared. I'm going to stop at 3. Plus 2 plus 1 squared plus 3 plus 1 squared. And if I simplify each of these, I get 1 squared plus 2 squared plus 3 squared plus 4 squared, just like this example here. And if you do the same exact thing in this one, you will find that it also equals this. So the same sum can be written in different ways. So some of the answers to our questions will have a few different answers. So let's give it a try. Now we want to write the sum using summation notation, and this is sometimes difficult, so just practice. Notice patterns. Notice how all of the denominators are 5. Well, that's helpful. That means that I'm going to have a denominator of 5. It's often helpful to just start at 1. Okay, so n equals 1. Well, let's just look at the numerators. What's happening here? Well, these are all even. If this is my first term, what if I say 2 to the first, 2 squared, 2 cubed, 2 to the fourth? Well, what's happening? Well, I have a base of 2 and I raise it to a power of n, whatever the term is. I have 5 terms, so I will end at 5. So this is the sum of this in summation notation. Let's try another one. Okay, now we have 5 terms. So the easy part is to say n equals 1 to 5. Okay, well now we want to figure out what's going on here. So just kind of analyze the pattern, see what's happening. Now I notice that these all can be written with a base of 2, like 2 to some power. So if this is n equals 1, this would be n equals 2, n equals 3, n equals 4, and so on. How do I get those numbers? Well, in order to get a fraction like this, I know that my exponent needs to be negative. In fact, if this is a negative 1, 2 to the negative 1 is the same thing as a half. Well, I also know that 2 to the power of 0 is 1. 2 to the power of 1 is 2. And I notice that this is my pattern. So how am I getting these exponents? Well, if this is supposed to be my first term, if I represent this as n minus 2, I get a negative 1 each time I get the exponent I want. So I can represent this sum as 2 to the n minus 2. There are other ways you can represent this. You could also say 2 to the power of n divided by 4, or you could say 1/4 times this. And there are a couple other choices, but these are the most obvious in my opinion. Okay, let's try this one. Now, notice how we have alternating signs. Because I have alternating signs in the odd terms are the negatives, I'm going to represent that piece as negative 1 to the power of n. So I know that that is going to be part of my summation. I have 4 terms, so I'll go from 1 to 4, and I have this piece. So let's just ignore the signs for a moment and see if we can come up with this other piece here. All right, well, notice up here, I have basically 2 to the first, 2 squared, 2 cubed, 2 to the fourth. So this is 2 to the power of n. Whereas on the bottom, I have 3 to the first, 3 squared, 3 cubed, 3 to the fourth. So this is 3 to the power of n. Well, you can write it this way, or you could say that this sum is equal to negative 1 to the power of n times 2/3 to the power of n. Or you can group these together and write this as negative 2/3 to the power of n as well. Any of these 3 answers would suffice. The last thing I want to mention are some properties of summation notation, and they're pretty straightforward. Basically, if you have a constant, you can multiply the sum by that constant. Here, basic distributive property types of properties like that. This concludes section 11.1.